Alibaba have released Qwen 2.5 Omni, which I think is the most multimodal of the open source models available today. I'm going to compare it with GPT-4o and Gemini 2.5 Pro. I'll then talk about the architecture and how it compares with Moshi and also Llama 3 before showing you how to run inference on Qwen 2.5 Omni on a GPU. And here is the model card, Qwen 2.5 Omni. It's a 7 billion parameter model. That's really just the parameters contained in the language model, because there are also adapters for vision, which allows for both images and video inputs, as well as audio on the input side. And then on the output side, it generates both text and streaming audio. So this is really a 4-way input if you consider image, video, text, and audio, and a 2-way output with text and audio. Now, I'm going to describe this in a little bit more detail. We'll take a quick look here at the files. You can see in total, it's roughly about 23 gigabytes in size, which is very large for a 7 billion parameter model, but that's because of the adapters that are there to be multimodal, and also due to the fact that some of those adapters are probably being stored here in 32 bits instead of 16 bits. Now, there's a technical paper that's been released, and this is probably the diagram to look at to understand the architecture. It has got multiple parts. It's not at all what I expected from a multimodal model. And it's unique in a few ways because, first of all, there's a split here in the middle. There are two rather large models. First of all, there's the Omni Thinker model, which is essentially a Qwen 7 billion parameter model. In fact, it started off as that model and then it was fine-tuned on top. So this was not trained from scratch. Then there's a vision encoder, which is taken from Qwen VL, the vision version of Qwen, which is multimodal but just image and text. And there's an audio encoder that converts speech into representations that can go into this language model here. And that audio encoder is from the Qwen audio model, which I did a video about earlier. So the inputs can be in form of video, vision or audio. If they are in the form of a video, then that video is split into frames. And there's a separation of about 40 milliseconds. So that means you've got about 25 frames per second that the video is converted to. And actually the audio from the video, if it's present, is also split up into frames like that, and it's fed in through the audio encoder. So in all, the Omni Thinker here is able to take in text tokens, but also representations of video, which is really images, and also audio. Now this transformer will then autoregressively produce the next text token. So it's operating to respond with text. But that's not where the model stops, because there's this whole stack up here that allows you to additionally generate audio. And the way that works is through a two-step process. You first have an Omni Talker model that creates audio output tokens, and those output tokens are then converted into waveform using this streaming codec out here. So this is a little bit reminiscent of how Moshi works, and I'll talk about that later. But this Omni Talker model, this is a smaller model than the Omni Thinker, and it serves only to create audio. It actually does create text tokens that are aligned with those audio tokens. So there's kind of text tokens being created by the Thinker, which are the ground truth or the most important output text tokens. But then kind of as a byproduct of producing audio tokens, there are also text tokens being produced here. Now, the model here, it's regressive and produces these output audio tokens. It is taking in the text tokens from the Thinker model, but it is also taking in hidden representations. That means it's taking in the vector representations all the way along here of the transformed inputs, in addition to the output text tokens. And this is all informing the audio that is to be generated on the next step. There's one more aspect that stands out as pretty unique in this design, which is the way that the positions are encoded for the audio and the text. You see, if you're playing a video or an audio file, the positions are really defined by time. When you're speaking, the gaps between your speech or the frames, the gaps between the frames, time is the concept that matters. Now, by contrast, in an LLM, there's no concept of time. In an LLM, you just have token positions. And actually, those positions are encoded. So when you convert text into tokens, you actually add in additional information to say what position that text is in relative to the rest of the sentence. And in the early transformers, you literally just put in some kind of numerical sequence to indicate the position. But over time, rather than putting in that concatenation of a position, it became more trendy because it was more effective to give an embedding to the token, but then rotate it according to where it was, rotate the vectors according to where the position of a given token is in the sentence. So if you have the cat is on the mat, at a very high level, the token for cat would be rotated a little bit, but mat would be rotated by more because it's later in the sentence. And this is how you encode the concept of positions in a language transformer. But if you move to audio, what you care about encoding is actually time. And so there's a special form of RoPE, which is rotational positional embeddings, and it's called TMRoPE, but it's time-stamped RoPE. So instead of just rotating based on position, there's also a rotation, and this is rotation in multidimensional space that's being used for the time. And this makes a lot of sense. When you have audio models or video models, I was always wondering, how do you convey that aspect of time to a model? It's not something that's explicitly conveyed or necessary in text models. I don't think it's even conveyed in Moshi. It's just implicit as far as I know. But it's here being made explicit in how the information is being encoded. So that's particularly interesting about how the vision and the audio encoders work here for Moshi. Now, just as a quick comparison, by the way, the audio encoder is essentially a whisper model. It is initiated as a whisper model, and then it's fine-tuned. This is a VIT, vision encoder model that also was taken from Qwen VL and then further fine-tuned in combination with the other parts here of the model. Now, just as a quick comparison with Llama, how does Qwen 2.5 Omni compare with Llama 3? Well, it's in somewhat similar. It's got this backbone of a language model, which is the thinker model here. It's got an encoder and adapter. This is the encoder here. There is actually an adapter layer. It's not shown, but there's an adapter layer between the whisper model and these embeddings. There's also an adapter layer here after the encoder, not shown. So it's very similar. This is the Llama 3 paper, by the way, and it's just showing the audio portion of the input. And then it's showing how there is a text-to-speech model. Now, this model was never released open source, so we don't really have the details. But at an architecture, from an architecture standpoint, it's fairly similar on the front end in how it takes in information for audio. I won't show the vision, but vision is basically the same and matches here. But it's quite different on the output because, well, we don't know what the exact text-to-speech model in Llama 3 is. But here it's a two-part system where we have a transformer generating a stream of tokens, which is very much like the Sesame model I made a video about recently, or also the Orpheus model. And then you decode that stream of tokens to get a waveform here. And then just very quickly to look at the Moshi paper. I am planning to do a video on Moshi. There's already inference scripts if you've access to the advanced transcription repo. That's the advanced voice product from Trellis. But the key difference with Moshi, not only does it adopt a tokens only approach, so it does not use any adapters here. It directly will encode the audio into tokens and feed those tokens as tokens, not as embeddings, like is happening here in Qwen. So Moshi will adopt, or does adopt, a tokens only approach. But furthermore, Moshi is quite unique in that it trains the model in duplex. What does that mean? It means it has actually two streams of audio that it is training on independently. It has one for the user and it has one for the assistant. And this is very beautiful because it means the model implicitly understands turn taking and understands noise and when to ignore noise and understands interactions between the speakers. And this is something that I don't think we've seen in any other open source. There might be some in literature, and I'd be very curious whether GPT-4o is in fact a duplex model or whether it's more of an adapter model like this. And one of the big questions is whether the Llama 4 model that comes out is going to be more of an adapter type model or whether it's going to be a full duplex model. It would be amazing if it was full duplex. Maybe the odds of it being full duplex have gone down just because Qwen have not gone full duplex. Also, it'll be interesting to what degree Llama 4 adopts a token-only architecture. You can see the output side here is becoming token-only, but the input side here is still relying on these embeddings going in here. So you don't have symmetry between input and output. The audio tokens at the output are only used for the output. There's no encoding from audio into tokens on the input side. Now, I'm going to show you how to inference this model, Qwen Omni. But first, let's just take a look at the inference of a model like GPT-4o if I input a video. And let's see what the inference of Google, the Gemini 2.5 Pro model is, which is available experimentally from AI Studio. Now, I'm going to upload here a small video. It's just, I think, 1 minute long to GPT-4o. And this video here it's a snippet from an earlier YouTube video on how to inspect an MCP server. And I'm going to ask what's happening in the video, who and what do you see, and what is it about? So a video will upload here with ChatGPT, but the 4o model, it's not natively set up for video, but it can take in video because, of course, you can split any video into images and you can feed the images in. So if a model can accept images, you can always make it a video model. And the same if a model can accept audio, you can always strip the audio from the video and feed it in. So the funny thing here is GPT-4o is currently extracting some clips. It's probably going to fail because it's not going to be able to run Whisper to extract the audio. Yeah, so we're hitting an error here. But if I say focus on the images, I think it will be able to extract some of the images and we might be able to feed those in and get some feedback. So GPT-4o has extracted some frames from the video and it's currently taking a look at those frames and it's saying it's a screen recording or demo. Now, it's not clear whether GPT-4o was trained on videos, whether there was a pipeline that extracted frames and did the training. You can, as I said, convert any model that takes in images to a video model, but it won't necessarily be good at video unless it's seen video type content. And I think Gemini has pretty much surely seen a lot of video content. And let me try the exact same question here. So while the video is uploading, I'll just go and copy the exact same question and I'll type it in here. One nice thing about Gemini is when it uploads, it tells you how many tokens the equivalent upload is. So it'll extract this, and I think it's going to be like 40,000 tokens. Yeah, 45,000 tokens. So it's converted the video and the audio and my text into tokens. And now it's going to run. And this model here actually does some thinking, which is not what I would have guessed initially because it doesn't have a thinking tag on it. And the thinking is actually fairly comprehensive. So Google has recently moved to reveal quite a bit more of its thinking thoughts. I think this literally is what the model is thinking. It's not trying to hide it as a summary. So maybe some influence from DeepSeek there. And yeah, it's got a presenter. So it's got me, the screen recording. It's talking about Microsoft Playwright MCP. And yeah, I would say this is a very detailed description. It's even describing entering a URL. So it's picking up the URL correctly and clicking Run Tool. So the Google model is indeed very multimodal and performs very well. Now, I'm not sure if in this interface I can get an audio output. So it's maybe not going to do what Qwen will do. But with Qwen, we're going to try do the same thing, upload the video and get it to output audio instead of text. And we'll see how it compares in terms of describing this video. So to run all of these scripts, I'm going to use some I have prepared available over at Advanced Transcription. So if you go to trellis.com/advanced transcription, you'll see here a link. There are some scripts for Moshi for inference already in the Moshi, in the Omni branch, and I'll be uploading some fine-tuning scripts there. But for today, we're focused on Qwen 2.5 Omni and running inference there on a GPU. So I've cloned that into Cursor, and within the speech-to-speech folder, we'll find Qwen 2.5 Omni, and within this, we're going to look at the README. So here in the README, we're going to start with the setup, but actually I want to run this on a GPU. So I'm going to set up on a RunPod instance, and I'll actually just put in a link here. So there's a one-click template that you might want to use. So I'm going to just click on that template. It will bring me to a RunPod instance. And I'm going to run on a H100 PCI. Actually, you need quite a bit of VRAM for this model. You probably need to have over 30 gigabytes, maybe even 40. And the longer the video you upload, it takes a lot of context, takes a lot of KV cache. So you need to have a fairly big GPU. I recommend one with 80 gigabytes, so an A100 or a H100. So Qwen 2.5 Omni. And if you want to look at the template, we're running PyTorch with CUDA 12.1. And we have plenty of space here. That's more space than needed. Probably only need 50 gigabytes. Even that's going to be safe. And we'll set the overrides and start this container. Now, once that starts up, we'll connect via SSH. So we're going to copy the SSH command, go to cursor and connect to host, add a new SSH host, and make sure you put in the right ID for your SSH key. That should be on your local computer. You will need to add the public key into RunPod. So I'll add that and connect, continue. And when VS Code is downloaded, I'm going to decide to clone a repo, and I'll clone from GitHub the advanced transcription. I'm going to rename that soon to advanced audio because it includes speech to speech, text to speech, speech to text, turn detection. And I'm going to clone it inside the workspace folder here and open it up. Now, once we're within the Qwen 2.5 Omni folder within speech to speech, we can start doing our installs. I'm going to make sure I CD into the right folder. Let me increase my screen size here. And I'm going to use UV because it's a lot faster than using pip. So I'll go ahead and get the installs going. Sound file, Qwen Omni utils. These are some utilities from Qwen that are recommended. HF transfer for fast download. And we're going to install that into the system, not a custom environment. Typically, if you're on a rented GPU, it can be good just to install into the system directly. So there's a range of installs and uninstalls that have to be done next. Basically, you need to be on a specific version of Transformers, which is this one here. And you also need to have a very recent version of Torch. If you use an older version of Torch, you can hit issues. Flash attention will work if you're on an A100 or a H100. And we also need to install Accelerate. So I'm going to run all of these. And this will take a moment. Then I'm going to install FFmpeg. That's going to be for managing audio. And I'm going to export this environment variable. I think the variable, I'm not sure if HF transfer works. I know for sure HF hub enable HF transfer works for sure, but this allows fast downloads, which we want. And when that's done, I'm going to run through Inference with an audio input to get an audio output. And then I'm going to run with a video input, the same query that we ran with OpenAI and with Gemini, and we'll also get an audio output. So we're going fairly full multimodal when we do the video input. Now, while the installs are working, I'm just going to upload the video. So I'm uploading that how to inspect an MCP server video. And I'm actually going to delete this input video here because I'm going to rename the other one as input. So it looks like our installs have gone well. We're going to install FFmpeg, and then we're going to enable HF hub, enable HF transfer. And this here can be renamed to input, input.mp4. That's how we have to name the input video. And also we have to name the input audio, which is going to be for the first test. Yeah, this is just my video here on finding on MCP servers, how to inspect. And here's some input audio, which we're going to listen to now. This is how you count to 3. 1, 2, 3. So that's me saying this is how you count to 3, 1, 2, 3. And we're going to put that as an input and see what we get as an output. So we're just feeding that audio into Qwen. I'll go through the script now momentarily. Let's just get it running in the meantime. And actually, I'm going to stop that because I need to first export this environment variable. And then I'll run the script. And while that's running, it'll take a bit of time because it has to download the model, and then it has to load the shards, and then it has to run inference. We'll take a look here. It's quite a simple script, and it's based on what's in the model repo card with just a few tweaks. We're loading the model, automatic torch dtype and device selection. We're using flash attention. I noted some issues there. Flash attention is actually working. So there are parts of the model, I think it's the audio decoder that's still in 32 bits and may not be using flash attention. It's using eager, but it is working mostly. So I recommend keeping that if you have a H100 or an A100. It's loading the processor, which contains tokenizers, and it's got then a conversation that's being fed in. So there's a boilerplate system message that we should include, otherwise it'll affect performance. And then we're just passing in here some audio. I'm not even passing in some text here. If I wanted to add some text, I could just add in here, type text, hello, how are you? But I'm not even going to do that. I'm just going to pass in the audio on its own. Then the text is going to be processed through the chat template. And here we're literally just templating, we're not tokenizing. And later we're going to pass in the text to the processor. We're preparing the audio, images, and video. Now we've got use audio and video turned to false. It doesn't matter if it's true or false because we have no video input. So really this is just preparing the conversation up here, which only has audio right now. And then it's passing all of these inputs, text, audio, images, videos, into the processor. And then it's putting them onto the right device in the right D type. I'm starting a timer to measure how long it takes. And then we're going to generate some outputs and decode them to see what the printed text is, because it's going to generate text. And then we're also going to save the audio. So here is where we're writing the audio to a file. And you can see that we have both an output of text IDs and of audio. So that's what makes it multimodal output. Normally this would just be outputting text IDs, but here it's outputting audio too. All right. So it looks like there's an issue finding the last of those safe tensors. Yeah. And the problem here is it's actually downloading the model to the container. Here, if we just export HF home and we want it to be workspace. So we basically want to download it to a directory that's on the hard drive that's connected to the instance. So here, if I run again, I need to first run this. And now we should see hopefully that, yeah, we've filled up the container because the model is not being downloaded to the right location. Okay, and the model has now loaded the shards and generated in 13 seconds. So yeah, it's not particularly fast. 13 seconds basically to generate all of this text here, which is not all that long. We can play the output, audio output here.
That's right. It's a simple and common way to count. Do you have any other questions about counting or numbers? That's right.
So it's a very sensible response based on the fact that I just counted out some numbers. It said, she said, that's right. It's a simple and common way to count. By the way, you can swap from a female to a male voice if you control the speaker embeddings, and that's controlled down here. So if I comment in speaker Ethan, that's going to move to a male voice. By default, it's the female voice. You can find the female voice name on the model card, but that's, you would comment this out and then comment in Ethan if you wanted to change that. So now let's move to the video test, and we'll input a video that I've uploaded, and we'll see what kind of quality output we get compared to, say, the Gemini model. And for this, all I need to do is run the following script. Let's see where it is. Down here, UV run video, and optionally you can pass a path, but by default it will just run on input MP4. So I'm going to paste that down here and run. And the model's already downloaded. So, you know, that's going to run with a default prompt, but we want to run with the Gemini prompt. So let me go back and get the exact prompt here. And then let's paste it in here. So we'll pass the specific query to this. So we're passing in the video and the query. And I've also got this truncate argument. This allows you to cut the video to the first 30 seconds. And yeah, it's going to help us not run over the memory limit. So otherwise, if you put in the full minute, even with 80 gigabytes, you're probably going to run out of VRAM and it's just going to have a CUDA error. So the truncate parameter allows you to cut that. So here it's loading the shards and it's now reading the video and it's running inference. In the meantime, we'll take a quick look at the video script here, which is quite similar to the audio script. There's a truncation function here. It just cuts the video to a maximum of 30 seconds. Then we've a parsing for the arguments for the input file, whether we want truncation and what the query is we're inputting. And then we go to loading the model. So again, using flash attention. When I run this script, I also print the architecture. We'll take a quick look at that. Then load the processor, which has the tokenizer. And now here's the conversation. There's the default system message here, which I haven't changed. Then there's some text. This is the query. And then there's the video. And yes, we're going to use audio and video. So that means that we're going to pass in the stripped audio. And actually the way it's passed in is it's in chunks of 2 seconds. So there are portions of the audio that are interleaved with the video in 2-second chunks. And yeah, if you want to get even more technical, in the encoder part of the model, that's before the main LLM part, the encoding is actually done with attention only within 2-second bands. So there's not global attention for the encoding. There is global attention within the LLM. So each token looks back at all past tokens, but for the inputs of video and audio, there's only 2-second attention within 2-second bands. So then we prepare the text, the audio, images, videos, which in this case are non-zero. These are meaningful. We prepare the inputs, and then we generate the text and audio outputs. And we write the sound file to file here as video output. So we've saved the video output here. I'd say the generation time, it's probably like a minute. I probably should put in a generation time measure. But here we'll take a look at, it's called video output, but it's a sound output. It's the audio output from the video. Let's listen to what's being said, and it should match what we're seeing here below. So I'll just increase the screen size.
Well, in the video, T here is a guy talking about the Model Context Protocol, MCP. He's explaining what tools the MCP provides and how you can use them. He mentions that you can use an MCP inspector, which you can run with npx. He also says that if you don't have npm installed, you should go ahead and install it. It seems like he's giving a tutorial or some sort of guide on using this EPP tool. So what do you think about it? Do you have any questions?
So the audio is pretty good. You notice that she said EPP for MCP, and it kind of butchered in this video the part here. But other than that, the audio is correct, and this certainly does describe the video. It's not as strong as Gemini Pro 2. It's not picking out exact websites. Now, granted, that might be in the second half of the video that was truncated. It's not quite as detailed and nice in its refined answer. But then again, Gemini Pro is an absolutely huge model. We don't know what size, but definitely way bigger than 7 billion parameters. So it's not exactly comparing apples to apples. Now, one last thing before I finish up here is to show you the architecture, which I printed out to file. And you can see the different parts of the model. There's the thinker model, which is literally a Qwen 7b model with 32 layers. You can see here it's got the linear layers and the attention then. And then you can see all of, that's actually the audio tower. So this is not the LLM part. There's 32 layers of what's basically a whisper model. My mistake there. Then you have an average pooler and a projection. So this is basically the adapter that's connecting the audio tower into the language model part. We also have a visual encoder, which should also have an adapter that I think seems to be called a merger. It's got 3 layers here. It's got a linear, Gaussian, and a linear to connect it onto the LLM. And then we do have the model. So this here, I think, is a version of the Qwen 7b model. And then lastly, we have the talker model, which is also a transformer architecture with 24 layers, followed by the decoder, the token to WAV. So it converts from tokens into waves. And yeah, this is really big, and there's a lot within the token portion here. You'll also see within that, there's the speaker, speaker encoder. So there's an input coming from a speaker that is ECAPA-TDNN. This is actually an embedding model. It allows you to convert somebody's voice into an embedding representation of that voice, its style. And that's how you can control whether you have the male or the female speaker. You're essentially inputting an embedding for that given speaker, and that's going through this speaker encoder model here. So that's the Qwen architecture, and that's how to run Qwen using audio as input, or to run Qwen using video, including audio and text as input, and getting audio and text as output. To wrap things up, what should you use Qwen 2.5 Omni for? Well, while it can be used for audio inputs and to generate audio outputs, it's maybe a bit slow in terms of latency. So the best use case is probably as an open source, and maybe the only open source model that can take in videos with audio and answer questions in text and as a bonus with audio. I will note that it's not supported on SGLang or on VLLM, so while you can run inference fairly easily as I showed you today, it's tougher to scale things up if you want to operate at larger batch sizes. That's it for this video. I'll put the key links below in the description. And if you have any questions, let me know in the comments.